Statistical test selection. Statistical analysis involves collecting data samples in a set of categories from which a sample can be drawn. A sample in statistics is a representative selection drawn from a total population. There are two types of statistical data normally distributed, which include parametric tests and not normally distributed data that include non-parametric tests. Central tendency is statistical measure that identifies a single value as representative of an entire distribution. It is a summary statistic that represents a central location of a distribution. The central tendencies are measured through the mean, median, and mode. The mean, median, and mode are all calculate the location of a central point using a different method. The mean is the average, where you add all the numbers and then divide by the number of numbers. The median is the middle value in the list of the numbers. To find the median, your numbers have been listed in numerical order from the smallest to the largest, and then the middle number is your median. The mode is the value that occurs most often. If no number in the list is repeated, then there is no mode for the list. However, in skewed distribution, this means the mean can miss the mark and falls outside the central area. This problem occurs because outliers have a large impact on the mean. Abstract values in an extended tail pull the mean away from the center as the distribution becomes more skewed and the mean is drawn further away from the center. Dispersion, standard deviation, is where there are normal distributions with the same mean but different variability. There are three common measures of dispersion, which are standard deviation, interquartile range, and range. Standard deviation is a typical difference between each data point and the mean. When the values in a data set are closer together, you have a reduced standard deviation. However, when the values are spread out more, the standard deviation is bigger because the standard deviation is larger. Secondly, the interquartile range is the measure of statistical dispersion, being equal to the difference between the upper and lower quartiles. There are four quartiles. The lowest quartile contains a quarter of the dataset, the smallest values. The upper quartile contains the quarter of the quarter of the dataset with the highest values. The interquartile range is the middle half of the data that is in between the upper and the lower quartiles. Finally, the range is the difference between the highest and lowest values within a set of numbers. To calculate the range, you have to subtract the smallest number from the largest number in the set. However, it is very susceptible to outliers, like the mean. Interferal stats. Statistical test analysis. Most research will look at statistical significance of conclusions of your findings. However, it isn't enough to say that data and findings are significant without performing statistical tests. The significant data that is produced and concluded of an experiment by using p-value, which is 0.05. If the p-value is below 0.05, then the data is considered meaningful. But if the data is above 0.05, then it's considered non-significant. The practical significant can potentially change the independent variable and is potentially significant, but it's not mathematically significant. For example, if you have an independent variable of Lucozade and wanted to test the effects it had on the sit and reach test, then you would measure the young British female gymnast without any consumption of Lucozade on the sit and reach test, and then you would measure when they had consumption of Lucozade after. If they If their flexibility increased after they had taken the Lucozade, then this would be practically significant, but not mathematically significant. Hypothesis testing. There are two types of hypothesis testing, which are null hypothesis and alternate hypothesis. A null hypothesis shows that there is no statistical significance between two variables and that no variation exists between variables, or that a single variable is no different than its mean. For example, if one British gymnast is given Lucozade before a routine, their performance will be the same if the British gymnast wasn't given any substance. Researchers try and disprove the null hypothesis to show that there is a relationship between the two variables in the hypothesis. The alternate hypothesis is the opposite of the null hypothesis, because it shows that there is a statistical significant relationship between two variables and it is testable. And an educated guess in the research. For example, if one British gymnast is given Lucozade before a routine, their performance will have a different outcome to the British gymnast that wasn't given any substance. There are two types of alternate hypothesis, which are directional and non-directional. Non-directional hypothesis predicts that the independent variable will have an effect on the dependent variable, but the effect is not stated. Directional hypothesis predicts that the independent variable will have an effect on the dependent variable and specifies the direction of the relationship. For example, if some young British gymnast had taken caffeine before a routine and had a better score than when they didn't take caffeine, and the researchers said that it was because of the caffeine, this would be directional. But if the researchers didn't know why the score had increased, then this would be non-directional, a non-directional hypothesis. Statistical test analysis. If you want to see whether there is a null or alternate hypothesis, then we need to use the p-value. If the score from the test is lower than the p-value, which can change, but in this case is 0.05, then we can reject the null and accept the alternate, because there is a significant difference and therefore there is no lock involved. However, if the p-value is equal to or bigger than 0.05, this accepts the null and rejects the alternate, because there is no significant difference. Therefore, the test has insufficient evidence of a relationship between the variables. The p-value can vary from size, but the lower the p-value, the more evidence there is to prove that the result is no luck. Dependent t-test. Once we have established whether there is a relationship or difference between the variables, this enables us to work out which test is appropriate for us to use in our research. For example, in this case, there is a difference in the research, which would then lead to you measuring how many factors are affected. In this case, we are going to assume there is none. There is one. This will lead you to the stage of using the same subjects or different subjects. And for this example, we will be using the participants for before and after the dependent variable is affected. This will then lead us to two paths, the parametric and non-parametric path. We will be taking the parametric test because parametric tests assume that data is normally distributed. Also, it is robust to variations of non-normality, so the data only needs to be approximately normally distributed. And compared to non-parametric tests, they are more powerful because they are more likely to detect true differences or relationships that exist. And therefore, this will lead us to the dependent t-test, which is a test we will be using if we were to go down this path. The independent t-test. Like the dependent t-test, we need to establish whether there will be a correlation or difference in the research. For the independent t-test, there will be a difference, which would then lead you to measuring how many factors are affected within the hypothesis. In this case, we are going to assume there is one. This will take you to the stage of using the same subjects or different subjects, and for this example, we will be using different participants for before and after the dependent variable is affected. This will take us to two paths, the parametric and non-parametric test. We will be taking the parametric test because we are researching the independent t-test, which goes down through the parametric test. Parametric tests assume that data is normally distributed. Also, it is robust to variations of normality, so the data only needs to be approximately normally distributed. And compared to non-parametric tests, they are more powerful because they are more likely to detect true differences or relationships that exist. This will lead us to the independent t-test, which is a test we would need if this was a route we had to go down, or that we had predicted in our research, to take in our research. Spearman's rank order test. Spearman's rank order collection test, like the previous test, has a specific route that the researcher needs to go down in order to be able to use this test. However, the path itself is much different from the first four tests. This is because Spearman's rank collection test has a correlation. However, because of this correlation, we don't need participants in the research. So once you have found it's a correlation, this takes you down the parametric path because the data is normally distributed. It is robust to variations of non-normality, so the data only needs to be approximately normally distributed, and this is more powerful than non-parametric tests because they are more likely to detect true differences or relationships.